In this question, we were told that a bumper car with a mass of 400 kilograms is going to strike another bumper car also with a mass of 400 kilograms. The first bumper car is moving rightwards at 6 meters a second, and the second bumper car is moving rightwards at 5.6 meters per second. They are going to collide, and then they are going to move apart, but we do not know what their final velocities are going to be. So this here is photo 1, corresponding to before the collision, and photo 2 is after the collision. I'm going to set my origin to be at the point of the collision, and I'm going to set rightwards as my positive axis. Now, because this is an elastic collision, we were told it was elastic, that means we're going to need to solve for both momentum and energy. Let's start with momentum. In the interest of space, I'm going to condense down some of the calculations and leave out a couple of steps here and there. So try to follow along as best you can. Conservation of momentum tells us that the total momentum in photo 1 must equal the total momentum in photo 2. So the total momentum in photo 1 is, I'm going to call the left car L, and I'm going to call the right one car R. The total momentum of the two cars in photo 1 is the momentum of the left car in photo 1 plus the momentum of the right car in photo 1. And that's all equal to momentum of the left car in photo 2 plus momentum of the right car in photo 2. Expand this out. Momentum of the left car is mass times velocity. So that's 400 multiplied by a velocity of 6i hat plus mass of the right car is also 400 times a velocity of 5.6i hat. And all of that is equal to mass of the left car, 400, times the velocity of the left car, which is velocity of the left car in photo 2, plus mass of the right car, 400, times velocity of the right car in photo 2, which is also unknown. Now, let us start simplifying this. 400 times 6 is going to give us 2400 I hat, plus 400 times 5.6, I don't know that off the top of my head, is 2240. And all of that's equal to 400 times the velocity of the left car in photo 2 plus 400 times the velocity of the right car in photo 2. Let's simplify this. 2400 plus 2240 gives us 4640 I hat is equal to 400 velocity of the left car in photo 2 plus 400 velocity of the right car in photo 2. To make this still simpler, what I'm going to do is I'm going to divide 4640 by 400, so that this entire equation can be written in simplest terms. So that gives me, if I were to flip the sides over here, that would give me velocity of the left car in photo 2 plus velocity of the right car in photo 2 is equal to 11.6 I hat. So this is our first relationship between these two quantities, the two velocities after the collision. Conservation of momentum tells us that they have to add up to 11.6 I hat. But that's as far as we can go with conservation of momentum. The next thing we have to do is apply conservation of energy. And the reason is we've now ended up with one equation with two unknowns. That cannot be solved. So conservation of energy has to give us more information. Conservation of energy in this case is going to tell us There's no potential energy, there's no work in, there's no work out, so the whole thing relies on kinetic energy. The kinetic energy of the left car in photo 1 plus the kinetic energy of the right car in photo 1 equals kinetic energy of the left car in photo 2 plus kinetic energy of the right car in photo 2. Expand this out. 1/2 times mass of the left car, 400, times velocity of the left car in photo 1 is 6 squared. Remember, kinetic energy is a scalar, not a vector. Momentum is a vector, kinetic energy is a scalar. There's no direction to kinetic energy. So that means that I don't need to write it as 6I hat. I can get away with writing it as 6. And my final answers for the different kinetic energies will also never have I hats or J hats in them. Plus 1/2 times the mass of the right car, which is also 400, times its initial velocity, 5.6 squared, is equal to 1/2 times 400 times velocity of the left car in photo 2 squared plus 1/2 times 400 times velocity of the right car in photo 2 squared. Now, let's start simplifying all of this. 1/2 times 400 times 6 squared gives us 7,200. Plus 1/2 times 400 times 5.6 squared is 6272. Is equal to half of 400 is 200 times velocity of the left car squared plus half of 400 again is 200 velocity of the right car squared. Now let's continue simplifying this. 7,200 plus 6272 gives us 13,472. And that must be equal to 200 times velocity of the left car squared plus 200 times the velocity of the right car squared. Next, let's divide everything by 200. 13,472 divided by 200 gives us 67.36. 67.36 is equal to velocity of the left car squared plus velocity of the right car squared. Okay, and this is as simple as we can make this equation. This is the relationship that conservation of energy tells us must exist between these two cars in this elastic collision. Now, finally, we have two equations and we have two unknowns. So we can go about solving these. Here's how I will do it. I'm going to rewrite this equation so that I subtract velocity on the right side, velocity of the right car from both sides. So this gives us velocity on the left side equals 11.6 minus velocity on the right side. I'm going to do away with the I hat over here just for a little bit until such time as it gets restored at the end. The reason for that is that you can get away with not having it when you put it into the energy equation because, again, energy is a scalar. So, substituting this into this equation that we got from energy, we get 67.36 is equal to velocity of the left car is 11.6 minus VR2 whole squared plus velocity of the right car in photo 2 squared. Expand this out. 11.6 minus velocity of the right car in photo 2 multiplied by 11.6 minus velocity of the right car in photo 2, because we're squaring it, it's the same thing as writing it twice, plus velocity of the right car in photo 2 squared. So now we have substituted this in and we have solved out for what the We have expanded this out, and we are ready to actually perform the squaring using FOIL. So 11.6 times 11.6. So because the rule of FOIL is firsts, outsides, insides, lasts. So first, 11.6 squared gives us 134.56. Minus outsides. You have 11.6 times negative VR2. That gives us negative 11.6 VR2. Minus insides, 11.6 times VR2. 11.6 times VR2. VR2 times VR2, which is plus VR2 squared. Plus VR2 squared. So, what are we going to do now? We are going to simplify this entire equation that we have here. Remember that this whole thing was equal to 67.36 the whole time. We are now ready to simplify this and combine all the like terms. So VR2 plus VR2 is going to give us 2 VR2 squared minus 11.6 minus 11.6 is going to give us 23.2 VR2. 134.56 minus 67.36, because I can now subtract this from both sides, gives us 67.2. Plus 67.2 is equal to 0. So now, this is the simplified version of that quadratic equation. And it is a quadratic equation, and although at worst these might be somewhat tedious to solve, they are all eminently solvable. So this is the quadratic equation we have ended up with. In the interest of space, I'm going to use the quadratic equation solver in my calculator. So, the coefficient of the r squared term is 2. The coefficient of the r term is negative 23.2. And the coefficient of, the constant term is 67.2. So we get that VR2 equals 6 or VR2 equals 5.6. So from quadratic formula, we get VR2 equals 6 or VR2 equals 5.6. And this, of course, is how fast it's moving. This would be in the I-hat direction. Now, let's look at something. The original velocity of the right-hand car was 5.6. So its velocity after the collision cannot also be 5.6. That means that VR2 must be 6 I-hat. Very good. And now we can use this equation over here, which related VR2 and VL2. And we can say that VL2 equals 11.6 I-hat minus VR2, which was 6 I-hat, which gives us 5.6 I-hat. So that is the speed of the velocity rather, of the left-hand car after the collision takes place. Now look at that. Initially, the velocities were 6 and 5.6 for left and right respectively. After the collision, it's 5.6 for the left car and 6 for the right car. It's the same velocities, but they've traded places. This is a pattern which I think it is the right of every physics student to discover for themselves, which is when two objects have the same mass and they have an elastic collision, the velocities trade places. They swap their velocities. This is a pattern that always applies, and it is through conservation of momentum and conservation of energy that you will always end up with a quadratic that represents this. In this question, we have a ball which has a mass of 0.3, which is initially traveling at 3 I hat meters per second, that is 3 meters per second rightwards. It's going to strike another ball which has the same mass, 0.3, which is initially at rest. This is photo 1. The first ball, so let me give these guys different colors. Let's say that I give a red shading to the first ball, and I leave the second ball uncolored. The first ball is going to, after the collision, travel upwards in this direction. And the second ball is going to travel downwards in this direction. Now, I'm going to set my origin and axes as follows. This is going to be my photo 2. We were told that this ball here is going to travel with a velocity of 0.5 at an angle of 50 degrees above the horizontal. And we need to find out what is the velocity of the second ball, the ball which I have not shaded. Now, I made a mistake when I was assigning this question. I told people to reference the wrong part of the video. And so some of you might have gotten confused about what this question was supposed to look like. The two balls don't move off together in the same direction. They move off separately. One goes up and the other one must go down. So that being the case, because that was my mistake, I'm going to turn this question into an extra credit. Anyone who got it right will get the points, and anyone who got it wrong because of that misunderstanding is not going to have anything deducted. Regardless, this is the correct way to solve the problem. This question is very similar to a scattering question that we saw in inelastic collisions. The first thing, as you probably guessed, that we need to do is we need to take this velocity vector, 0.5 meters per second at 50 degrees, and break it into its x and y components. So the velocity of ball 1 in photo 2 in the x direction is going to be equal to 0.5, sorry, this is the y direction, is equal to 0.5 times the sine of 50 degrees, which is 0.383. And the horizontal velocity of ball 1 is going to be 0.5 cos 50 degrees, which is 0.321. Now that we have this information, let us use conservation of momentum to solve for what the final velocity of this ball must be. Conservation of momentum tells us that the total momentum in photo 1 is equal to the total momentum in photo 2. Let's expand this out. The momentum of ball 1 in photo 1 plus the momentum of ball 2 in photo 1 is equal to the momentum of ball 1 in photo 2 plus the momentum of ball 2 in photo 2. Expand still further. The mass of ball 1 photo 1 times the velocity of ball 1 photo 1 plus the mass of ball 2 photo 1 times the velocity of ball 2 photo 1 is equal to mass of ball 1 photo 2 velocity ball 1 photo 2 plus mass of ball 2 photo 2 velocity of ball 2 photo 2. Now let's start plugging in everything that we know. The masses of these two balls are of course the same thing. They're both 0.3. The initial velocity of ball 1, initially it's moving in just the x direction, something like this. So its initial velocity is 3 hat plus mass of ball 2 in photo 1, 0.3, times its initial velocity, which was 0, is all equal to mass of ball 1 in photo 2, 0.3, times velocity of ball 1 in photo 2. So the velocity of ball 1 in photo 2 is horizontally 0.321, and vertically 0.383. So we would express all this as 0.321 I hat plus 0.383 j hat plus mass of the second ball, 0.3, times velocity of the second ball. Okay. Now, let us simplify this. 0.3 times 3 I hat, that's 0.9 I hat. This term obviously is going to disappear because it's just 0. 0.3 times 0.321 0.3 times 0.321 gives us 0.0963. So multiplying this across, we get 0.0963 I hat plus 0.383 times 0.3 gives us 0.1149. 0.1149 j hat plus 0.3 velocity of ball 2 in photo 2. Let's take these two terms and move them to the other side. That's going to give us 0.9 I hat minus 0.0963 I hat minus 0.1149 j hat is equal to 0.3 velocity of the second ball in photo 2. Now, we can combine the I hat terms, but we cannot combine an I hat term with a j hat term, obviously. It's like having two different variables. You can't add something in x with something in y directly. You can't add 2x plus 3y and end up with 5 something else. So we can just combine the I hat terms. That gives us 0.9 minus 0.963. That gives us, 0.9 minus 0.0963 gives us 0.8037. Finally, we can divide both sides by 0.3. So 0.8037 divided by 0.3 gives us 2.679. So the velocity of ball 2 in photo 2 is equal to 2.679 I hat minus 0.1149 divided by 0.3 gives us 0.383. 0.383 j hat. So this then is the final velocity of the second ball. This is the velocity that it must have after the collision took place. And the solution to this entire question is almost identical to the way that we did it in the scattering question from a couple of videos ago when we were looking at inelastic collisions. Now, if we had not known that this was 50 degrees, then this would have become a considerably harder question to solve. And solving questions where three pieces of information are unknown, that is, not just x and y for one of the balls, but let's say the y direction for the second ball, are beyond the scope of this course. They would require some fairly significant geometry and trigonometry to solve. But these types of questions are pretty straightforward, and they are easily solved using the same techniques we used for scattering. In this question, we have a shell which is going to be launched off of the ground, which is going to reach its peak and then explode into three fragments. One of the fragments is going to land somewhere over here. It's going to travel rightwards, like so. And another fragment is going to travel straight upwards. The third fragment is going to travel straight downwards. So we have a fair bit going on over here. It would be nice if we could identify the fragments. So what I'm going to do is I'm going to color code them. The original fragment I'm going to color code in orange. The fragment that goes downwards, I'm going to color code in yellow. The fragment that went rightwards, I'm going to color code in blue. And the fragment that went upwards, I'm going to color code in purple. Okay. So, we can now take a couple of different photos of all of the things that are happening in this situation. Photo 1 is going to correspond to the original shell on the ground. Photo 2 corresponds to the shell reaching its peak over here. Photo 3 corresponds to the explosion, which, to make it a little bit more clear, I'm going to draw a circle around it to show where photo 3 is being taken. Photo 4 is going to correspond to the fragment traveling up, reaching its peak. And to make those a little bit clearer, I'm going to highlight those in red as well. And finally, photo 5 corresponds to the blue fragment landing on the ground over here. Okay, so there's a fair bit going on in this overall question. Let's put down more of the information that we know. The original fragment had a mass of 2 kilograms, and it was fired at an angle of 40 degrees with a velocity of 50 meters per second. So 50 meters per second at a velocity of 40 degrees. I'm going to draw my axes now. I'm going to set rightwards as being positive x, upwards as being positive y. I'm going to I'm going to break this into its components because this was originally given to us in polar. So we have to break this into its components. Now let's go ahead and do that. So this horizontal component is going to be 50 cos 40 degrees, which is 38.3. meters per second. Meanwhile, this side over here is going to be 50 sine 40 degrees, which is 32.14. Okay. Now, the fragment which traveled downwards, we were told that it had a mass of 1 kilogram and that it was traveling at an initial velocity of 10 meters per second downward, which would be negative 10 j hat meters per second. The fragment that lands in photo 5 had a mass of 0.7 kilograms, and therefore the mass that flew upwards must have a mass of 0.3 kilograms. Okay, a lot of information to keep track of in this question. But what we're going to see is that this can be solved pretty easily using the standard rules of kinematics and momentum that we have been exposed to for so long. So let us start by finding out what is the velocity of the 2 kilogram object just before the explosion takes place. To do that, we need to use kinematics between photo 1 and photo 2. Since it's being shot up at an angle, that means we need to follow it in both x and y, and we will need to calculate some of the kinematics quantities later. For the moment, I'll just leave empty spaces for now and we'll fill them in as we need to. So, this object, this 2 kilogram shell, is in projectile motion. And projectile motion means that it experiences no acceleration in x and an acceleration of 9.81, negative 9.81 in y. Its initial velocity in x was 38.3, and its initial velocity in y is 32.14. So, its final velocity in y, when we reach photo 2, is going to be 0, because photo 2 corresponds to the peak of this object's motion. So that means that in order to find out what the velocity is in preparation for a momentum calculation between photo 2 and photo 3, we're going to need to find out what is the x velocity of the fragment. And that is very easy to do. The velocity of the fragment in photo 2 has not changed in the x direction. Because the acceleration in x is 0, that means that the velocity in photo 2 is simply 38.3 I hat meters per second. Now, let us use this information in preparation for a conservation of momentum calculation. Conservation of momentum tells us that the momentum of the initial fragment, so that would be the momentum of the 2 kilogram object in photo 2, must be equal to the momentum of the remaining fragments in photo 3. So that would be momentum of the 0.3 kilogram object in photo 3 plus the momentum of the 0.7 kilogram object in photo 3 plus the momentum of the 1 kilogram object in photo 3. Let's start expanding some of these out. The momentum of the 2 kilogram object is given as mass 2, velocity 38.3 I hat, is equal to the mass of the 0.3 kilogram object times its velocity, we do not know that yet, let's just call that V of the 0.3 kilogram object in photo 3, plus the 0.7 kilogram object, so its mass is 0.7, times a velocity of 0.7, or the velocity of the 0.7 object in photo 3, plus the last object is a 1 kilogram object, and we know that this one moves downwards at a velocity of negative 10 j hat. Okay, so now let us start solving for these two unknown velocities. Two multiplied by 38.3 is going to give us 76.6. So, and that was going to give us 76.6 I hat equals 0.3 velocity of the 0.3 fragment in photo 3 plus 0.7 times the velocity of the 0.7 kilogram fragment in photo 3, and 1 times negative 10 will give us minus 10 j hat. Okay, the negative 10 j hat can be moved to the other side, and it'll help us at this time to realize that in this example, the 0.7 kilogram object is moving purely rightwards. There is no vertical component to how it's moving. Meanwhile, the 0.3 kilogram fragment is moving purely upwards. There's no horizontal component. So one way to go about solving this is to separate out all of the horizontal and vertical components. You're completely allowed to do this when you're dealing with i's and j's. So to simplify all of this, we can say that the horizontal momentum, which is 76.6 I hat, must be equal to the final momentum of the only object which is traveling horizontally. That is the 0.7 kilogram fragment. And we can say something similar, and so we can easily solve, first of all, for what the velocity of the 0.7 kilogram fragment is. The velocity of the 0.7 kilogram fragment in photo 3 equals 76.6 divided by 0.7. 109.43. In the meantime, with a little bit of rearrangement, we can look at the remaining terms and see how they are moving in the j direction. Remember, the 1 kilogram object was moving downwards in j, that's where this negative 10 j hat momentum came from. And the 0.3 kilogram object is moving upwards in j, and that must be the counterbalance to that. So moving these things around, we get 10 j hat is equal to 0.3 times the velocity of the 0.3 kilogram object in photo 3. So the velocity of the 0.3 kilogram object in photo 3 must be equal to 10 divided by 0.3, which is 33.33. J hat. So I realize that this particular calculation looks rather convoluted. Let's review this before we move forward. We started with conservation of momentum, which I've drawn in a rather unusual way. I've written things on separate lines because I want to save some space for the rather lengthy calculation which is going to come for the kinematics part of this, for the peak height and for the range of these two fragments. So let me put a dotted line over here showing where one line of this ends and another one begins. And again over here, corresponding to where we've plugged in all of the known information. And then over here, as we simplify, over here, as we broke out simply the x-coordinates by themselves, and we solved for the velocity of the 0.7 fragment immediately after the explosion. And finally down here we have the velocity of the 0.3 kilogram fragment immediately after the explosion. So, granted that my handwriting is terrible, but this is simply a explosion question. It is a conservation of momentum question, just like so many that we have seen before. Okay. Now let's go about solving for the. So first of all, these are the two answers for part A. These are the two velocities that were unknown. So 109.43 I hat was the velocity of the 0.7 kilogram fragment after the explosion, and 33.33 J hat was the velocity of the 0.3 kilogram fragment immediately after the explosion. Now, we were asked to find out what is the maximum height of the 0.3 kilogram fragment. This is a piece of cake, because we can easily solve for this using our standard kinematics. So for part B of this question, so this was part A, for part B, we have we can talk about all of the variables that are occurring in the y direction for this 0.3 kilogram fragment. So in the y direction, we have delta y, which is unknown. Its initial velocity, just before the explosion takes place, was 33.3 J hat. The final velocity is 0, because that's the velocity it'll have when it reaches the peak in photo 2. And the acceleration is going to be negative 9.81 J hat meters per second. So this is corresponding to photo 3 to photo 4. So we have two velocities, an acceleration, and we're looking for a displacement. We're looking for how high the fragment travels. There's only one equation that weaves together all four of these quantities, and that's toolbox equation number 4. V final squared minus V initial squared is equal to 2 times acceleration times delta y. Plug in everything that we know. V final squared, 0 squared minus 33.3 squared is equal to 2 times 9.81 times delta y. So 33.3 squared is going to give us 1,111. And this, by the way, should be a negative 9.81. So now I have negative 1,111 is equal to negative 19.62 times delta y, or delta y is equal to 56.63 meters. So this now is the displacement of the 0.3 kilogram fragment as it travels upwards from the explosion point. This is how far it gets above the point of the explosion. That's important. This is not how far it travels above ground level, it's only how far it travels above this level of the explosion. Finally, we have to look at the third fragment, the fragment that landed over here. This is moving in 2 dimensions at the same time, so we need to make another one of our 2-dimensional tables. So this is going to correspond to photo 3 to photo 5. It's going to include X and it's going to include Y. I'm going to draw another dashed line over here. And we're going to fill in the rest of our table. The displacement, the initial velocity, the final velocity, the acceleration, and the time. Okay. Now, we know that its initial velocity in y is 0, and its initial velocity in x was 109.43. We do not know what the final velocities are. We know the acceleration will be the usual 0 and negative 9.81, but now we're stuck. There's one more piece of information that we need in order to solve for any of this over here. Fortunately, we can go back to how the original 2 kilogram object was launched, and we can get that piece of information. What we need to know is how far did this fragment, this 0.7 kilogram fragment, fall between photo 3 and photo 5. And that's easy to do using the information that we already have in the first part of this question. We know the acceleration of this object because the height of this object must be the same as the height of the fragment in photo 2. And that just means that we need to solve for delta y over here. We know v initial, we know v final, we know acceleration, we just need to solve for delta y. And so we can use toolbox equation number 4 again. V final squared minus v initial squared is equal to 2 times acceleration times delta y. Now I only have so much space over here, so I'm just going to write this in a little bit of shorthand. V final squared is 0 squared minus v initial is 32.14 squared is equal to 2 times acceleration, negative 9.81, times delta y. So 32.14 squared gives us 1032, that's very close to 1033, equals negative 19.62 times delta y. Therefore, delta y is equal to 52.65. So that means that our fragment is going to fall by 52.65 meters. Its delta y is going to be negative 52.65. Okay, now we have something to work with. We have 3 pieces of information in y, and we can solve for the time. So the way we would do that is using toolbox equation number 2. Toolbox equation number 2 says delta y is equal to v initial times t plus 1/2 acceleration times t squared. Let's plug in everything that we know. Delta y is negative 52.65 is equal to v initial, 0, I'm not even going to bother with the t over there because this is going to cancel out anyway, plus 1/2 times acceleration, 9.81, times t squared. Okay, so half of negative 9.81 is 4.905. When we solve all of this out, we're going to get a time of let's see, negative 52.65 divided by negative 4.905, and finally take the square root, 3.28 seconds. Last of all, we now know the time we need to solve for the displacement in x, and the easiest way to do that is to use toolbox equation number 3. Delta x divided by time is equal to, or actually better still, toolbox equation number 2 would do better over here. Delta x is equal to v initial times t plus 1/2 at squared. So delta x is unknown, but that in turn is equal to v initial, which is 109.43 times 3.28 plus the acceleration here is 0. So this entire second term is going to work out to 0. So all we have to do is take that time multiplied by 109.43, and that gives us 358.52. So the distance that this fragment traveled from the explosion point to the point of landing was 358.52 I hat meters. This was a long question, but it was still solved using a combination of kinematics, conservation of momentum, and a bunch more kinematics. And so using all of this, we were able to solve for how high one fragment goes, and we were able to solve for how far another fragment goes after the explosion takes place.